So here's something to sit with as you settle in tonight. Right now, wherever you are, there are objects in the universe so strange, so fundamentally weird, that even the people who spend their entire careers studying them will openly admit they don't fully understand what's going on. And I don't mean they're being modest. I mean, some of the smartest physicists alive will look you in the eye and say, "Yeah, we're still figuring this out. We've been working on it for over 100 years, and the deeper we dig, the stranger it gets." Black holes. You've heard the name 1,000 times. You've probably seen those dramatic images, swirling disks of glowing gas, a dark shadow at the center, maybe from that famous photograph that made the rounds a few years back. But if someone asked you to actually explain what a black hole is, like really explain it, you might find yourself reaching for words and coming up a little short. And that's completely fine. That's actually where we're going to start tonight, right at the very beginning, with the simplest possible question. What even is this thing? And how did anyone first dream it up? Because here's what's kind of wonderful. The idea behind a black hole is, at its root, shockingly old. Way older than you'd expect. We're not talking about some concept that sprang fully formed from Einstein's brain in the 20th century. The seed of this idea goes all the way back to the late 1700s, to a quiet English clergyman named John Michell. And his story is one of those beautiful examples of someone asking a question so far ahead of its time that the world basically shrugged and forgot about it for over a century. John Michell was born around 1724, and he was one of those people the 18th century seemed to produce in abundance. A natural philosopher, which is what they called scientists back then, who was curious about absolutely everything. He studied earthquakes. He figured out a way to measure the force of magnetism. He built one of the first devices for measuring the gravitational attraction between small masses, a device that Henry Cavendish later used and got most of the credit for. Michell was brilliant, but he lived out in the English countryside, serving as a rector in a small parish in Yorkshire, and history has a way of being unkind to people who do their work far from the spotlight. But in 1783, Michell wrote a letter to the Royal Society, that's the prestigious scientific institution in London. And in this letter, he laid out an idea that, when you hear it, sounds almost absurdly modern. He was thinking about light. Specifically, he was thinking about how gravity affects light. Now, at this point in history, most people who thought about light at all considered it to be made up of tiny particles. Newton had championed that idea, and Newton's word carried enormous weight. So Michell took that assumption and ran with it. If light is made of particles, he reasoned, then those particles should be affected by gravity, just like everything else. A cannonball fired upward slows down because of gravity. So shouldn't a particle of light, leaving the surface of a star, also slow down a little? And here's where Michell's thinking gets really interesting. He asked, what if a star were massive enough and dense enough that the gravity at its surface was so strong that light particles could never escape? They'd fly upward, slow down, and fall back, just like a ball thrown into the air. The light would never reach us. The star would be completely invisible. Dark. A dark star, he called it. Think about what that means for a second. In 1783, before the French Revolution, before the steam locomotive, before anyone had the faintest idea what an atom looked like, a country parson in Yorkshire was sitting there working out that there could be objects in the universe so massive that nothing, not even light, could get away from them. That's essentially the core idea of a black hole, sketched out with nothing more than Newton's laws and a quill pen. Now, Michel didn't have all the details right. He was working within Newtonian physics, and the full picture of black holes requires Einstein's general relativity, which wouldn't come along for another 130 years. But the intuition, the central insight, that gravity could be strong enough to trap light, that was spot on, and almost nobody noticed. The letter was read, filed away, and largely forgotten. A French mathematician named Pierre-Simon Laplace independently came up with a very similar idea about a decade later, in 1796, and included it in his book on celestial mechanics. But Laplace actually removed it from later editions, possibly because the wave theory of light was gaining ground, and it wasn't clear that waves would be affected by gravity the same way particles would be. So the whole concept just kind of drifted into obscurity. And that's where it sat, gathering dust, for a very long time. The 19th century came and went. Physics made enormous strides. Thermodynamics, electromagnetism, the understanding of energy and entropy. But the idea of a star so dense that light couldn't escape, it just wasn't on anyone's radar. There was no framework to make sense of it properly. No mathematical language that could describe what would actually happen near such an object. It was a curiosity, a thought experiment that had been thought and then set aside. And then Albert Einstein changed everything. Not all at once, and not in the way most people imagine. The popular story is that Einstein just sat down and dreamed up general relativity in a flash of genius. But the reality is messier and more human than that. It took him about 10 years. 10 years of grinding, beautiful, sometimes agonizing work from roughly 1905, when he published his special theory of relativity, to 1915, when he finally presented the full field equations of general relativity to the Prussian Academy of Sciences in Berlin. Let's slow down here, because this is one of those moments where it's worth understanding what Einstein actually did, at least in broad strokes. You don't need the math. We're just going to talk about the idea, and the idea is genuinely one of the most stunning things a human being has ever come up with. Before Einstein, gravity was understood through Newton's framework, and Newton's version worked incredibly well for most things. It told you how planets orbit the sun, how apples fall from trees, how tides work. In Newton's picture, gravity is a force. The earth pulls on you, you pull on the earth, and this force acts instantaneously across any distance. It's clean, it's elegant, and for over 200 years, it predicted almost everything perfectly. But there were little cracks, tiny discrepancies. The orbit of Mercury, for instance, the closest planet to the sun, had a slight wobble that Newtonian gravity couldn't fully account for. It was a small thing, but it nagged at people. And Einstein, being Einstein, wasn't content to just patch the old theory. He wanted to rebuild gravity from the ground up. What he came up with is this: gravity isn't a force at all. It's geometry. Imagine you have a large, flat rubber sheet stretched out tight. Now place a heavy bowling ball in the center. The sheet curves, right? It sags around the ball. Now roll a marble across the sheet. The marble doesn't travel in a straight line anymore. It curves toward the bowling ball, following the warped surface of the sheet. To someone watching from above, it looks like the bowling ball is pulling the marble toward it. But the marble is just following the shape of the surface. There's no invisible force reaching out and grabbing it. It's the shape of the space itself that's doing the guiding. That's the core of general relativity, in the loosest possible terms. Mass and energy warp the fabric of space-time, not just space, but time too, and we'll come back to that. And objects move along the curves that this warping creates. The sun doesn't reach out and grab the Earth with some mysterious force. The sun's mass warps the space-time around it, and the Earth follows the curved path through that warped space-time. It's a completely different way of thinking about gravity, and it's more accurate than Newton's version in every measurable way. Now, Einstein published his field equations in November of 1915, and they were complicated. Really complicated. They're a set of 10 interlinked equations that describe how mass and energy determine the curvature of space-time, and solving them for any real situation is extraordinarily difficult. Einstein himself solved them only for simplified, approximate cases. He didn't think exact solutions would come easily if they came at all, which is what makes what happened next so remarkable. Within weeks, literally weeks, a German physicist and astronomer named Karl Schwarzschild found an exact solution, and the circumstances of this are almost unbelievable. Schwarzschild wasn't sitting in a comfortable university office. He was serving on the Eastern Front of World War I, stationed on the Russian front, doing artillery calculations for the German army. He was already suffering from a rare and painful autoimmune disease called pemphigus, which would kill him just a few months later, in May of 1916. And there, in the trenches, between artillery barrages, Karl Schwarzschild worked out the first exact solution to Einstein's field equations. His solution described the space-time geometry around a perfectly spherical, non-rotating mass. Think of it as the simplest possible case, a single, round, stationary object, and what the fabric of space-time looks like in its vicinity. And the solution was beautiful. It worked perfectly for describing the gravitational field outside a star, like the sun. It predicted the correct bending of light around massive objects. It nailed the orbit of Mercury. Einstein was reportedly delighted when he received Schwarzschild's letter. But there was something lurking in the math, something strange. Schwarzschild's solution contained a particular radius, a distance from the center of the mass, where the equations did something unsettling. At this radius, some of the terms in the equations blew up. They went to infinity. Mathematicians call this a singularity, a point where the math breaks down and stops giving you sensible answers. And this critical radius depended on the mass of the object. For the sun, it works out to about 3 kilometers. For the Earth, it's about 9 millimeters. Tiny, absurdly small compared to the actual size of these objects. Now, for a normal star like the sun, this radius is buried deep inside the star itself, far beneath the surface. So it didn't seem to matter much in practice. The solution only applied to the empty space outside the star, and the sun's surface is hundreds of thousands of kilometers from its center. That critical radius of 3 kilometers was a mathematical curiosity, nothing more. Nobody worried about it. But here's the thing that would eventually keep physicists up at night. What if you could somehow compress all of the sun's mass into a sphere smaller than 3 kilometers? What if a star could collapse so completely that its entire mass was squeezed inside that critical radius? What would happen then? That question, that deceptively simple question, would take decades to answer. And the answer, when it finally came, would be stranger than anything Michel or Laplace or even Einstein had imagined. Because what Schwarzschild had stumbled upon, almost by accident, in the middle of a war, while dying of a disease that was eating him alive, was the mathematical fingerprint of something the universe could actually create. The radius that bears his name, the Schwarzschild radius, is what we now call the event horizon of a black hole. It's the point of no return, Cross it and you're not coming back. Not you, not light, not information, not anything. But in 1916, nobody knew that yet. Nobody even believed such a thing could exist in nature. The math said it was possible, sure, but math says a lot of things are possible. The real question was whether the universe would ever actually produce conditions extreme enough to make it happen. And answering that question would require understanding something that no one in 1916 had a handle on yet. What happens when a star dies? Because it turns out that the story of black holes is, at its heart, a story about stellar death. About what happens when a star runs out of fuel and gravity, that patient and relentless force finally wins. And the person who would take the first real step toward understanding that, who would connect the dots between dying stars and Schwarzschild's strange radius, was a 19-year-old kid on a steamship crossing the Arabian Sea in the summer of 1930, scribbling calculations in a notebook while the other passengers played cards and watched the coastline slide by. His name was Subrahmanyan Chandrasekhar, and he was on his way from India to England, to Cambridge specifically, to begin graduate studies in physics. He'd won a scholarship, a government scholarship that was a very big deal at the time, and he was headed to work under Ralph Fowler, one of the leading figures in the new quantum mechanics that was reshaping physics. But Chandrasekhar wasn't the kind of student who waited for the semester to start before he started thinking. He had weeks on that ship, and he had a question that was bugging him, and he had a pencil and a notebook. And honestly, what else are you going to do on a steamship crossing the Arabian Sea in the heat of summer? Here's what he was thinking about. A few years earlier, in the mid-1920s, physicists had started to figure out what keeps a dead star from collapsing. See, when a normal star like the Sun is burning, fusing hydrogen into helium in its core, the outward pressure from all that nuclear energy balances the inward pull of gravity. It's a tug of war, and as long as the fuel lasts, neither side wins. But eventually, the fuel runs out, and when it does, gravity starts winning. The star contracts, it shrinks. And the question is, how far does it shrink? Does it just keep going forever, getting smaller and smaller until it's a point? Or does something stop it? By the late 1920s, the answer seemed clear, and it was reassuring. Ralph Fowler himself had worked this out. When a star collapses and its matter gets squeezed incredibly tight, the electrons in that matter start pushing back. Not because of any chemical bond or electromagnetic repulsion in the usual sense, but because of a quantum mechanical principle, the Pauli exclusion principle, which says that no two electrons can occupy the exact same quantum state. When you pack electrons closer and closer together, they resist. They generate a pressure called electron degeneracy pressure, and this pressure doesn't depend on temperature. It doesn't need fuel. It's just a fundamental consequence of quantum mechanics. And it was enough, Fowler argued, to hold up a dead star against gravity. The star would shrink down to something small and dense, what we now call a white dwarf, and then it would just sit there, slowly cooling, forever. Problem solved. Gravity doesn't win. The universe is safe. And that was the accepted picture when Chandrasekhar boarded that steamship. But he was a careful thinker, and he noticed something that Fowler had glossed over. Fowler's calculation treated the electrons as if they were moving slowly compared to the speed of light. That's fine for a modestly compressed star. But what about a really massive star? A star with, say, twice the mass of the Sun, or 3 times? When that much mass collapses, the electrons get squeezed so tightly that they're forced to move incredibly fast, close to the speed of light. And when particles move that fast, you can't use ordinary Newtonian mechanics anymore. You need special relativity. Chandrasekhar, sitting on the deck of that ship with the Indian Ocean stretching out around him, started redoing Fowler's calculation with relativistic corrections. And what he found changed everything. When you account for relativity, the electron degeneracy pressure doesn't increase as fast as you'd expect. It still increases as you compress the star, but gravity increases faster. And there's a tipping point, a specific mass above which the electron pressure simply cannot hold the star up, no matter how dense it gets. Chandrasekhar calculated that mass. He found it was about 1.4 times the mass of the Sun. Below that limit, a dead star can settle into a comfortable retirement as a white dwarf. Above it, the electrons lose the fight, gravity wins, and the star has to keep collapsing. Think about what that means. A 19-year-old on a boat with a pencil had just discovered that there's a maximum mass for a white dwarf. And if a star exceeds that mass, physics, as anyone understood it in 1930, offered no known mechanism to stop the collapse. Nothing. The star would just keep falling inward, getting denser and denser, and nobody could say where it would end up. This number, 1.4 solar masses, is now called the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. It's the dividing line between stars that die quietly and stars that die in ways that force us to confront the most extreme physics in the universe. And Chandrasekhar figured it out before he even arrived at Cambridge. Now, you'd think this would have been celebrated. You'd think the physics community would have said, "Wow, this young man has discovered something profound. Let's explore this further." But that's not what happened. And the reason it didn't happen has a lot to do with one person, Arthur Stanley Eddington. Eddington was, at the time, probably the most famous astrophysicist in the world. He was the man who had confirmed Einstein's general relativity in 1919 by measuring the bending of starlight during a solar eclipse, an expedition that made Einstein a global celebrity overnight. Eddington was brilliant, charismatic, and enormously influential. He was also, it turned out, deeply uncomfortable with what Chandrasekhar's calculation implied. Chandrasekhar spent the next few years at Cambridge refining his work, making it more rigorous, checking and rechecking. By 1935, he was ready to present his results formally to the Royal Astronomical Society in London. He gave his talk. It was clear. It was mathematically solid. It was important. And then Eddington stood up. What happened next is one of the most painful episodes in the history of 20th century physics. Eddington, without warning Chandrasekhar beforehand, which was a serious breach of scientific etiquette, publicly attacked the entire result. He didn't just disagree with the math. He mocked it. He called the idea of a star collapsing without limit absurd. He said there ought to be a law of nature preventing it. He used his enormous prestige and his considerable rhetorical skill to essentially dismiss Chandrasekhar's work in front of the entire assembled community. And here's the thing. Eddington didn't have a rigorous counter-argument. He didn't point to a flaw in the equations. He just felt, on some deep intuitive level, that the universe shouldn't work that way, that it was too disturbing, too messy, too strange. A star collapsing forever? No. Nature must have a way out. He was sure of it. The effect on Chandrasekhar was devastating, not because Eddington was right, he wasn't, but because Eddington was so powerful. When the most famous astrophysicist in the world publicly ridicules your work, people listen. And many physicists, rather than carefully evaluating the math, simply deferred to Eddington's authority. Chandrasekhar, deeply hurt and frustrated, eventually abandoned the topic of stellar collapse altogether. He moved on to other areas of astrophysics, stellar dynamics, radiative transfer, and did brilliant work in those fields. He'd eventually win the Nobel Prize in 1983, partly for the very calculations that Eddington had ridiculed. But the damage was done. The question of what happens to stars above the Chandrasekhar limit, the question that pointed straight at black holes, was effectively shelved for years. Now, let's sit with that for a moment, because it tells you something important about how science actually works. It's not always this clean, rational process where the best ideas win on merit. Sometimes the best ideas get buried because the wrong person has too much influence. Sometimes progress stalls for a generation because of ego or fear, or just the sheer human discomfort of facing something that doesn't fit your picture of how the world should be. Eddington wasn't a bad scientist. He was a great scientist who happened to be wrong about this one thing, and his wrongness, amplified by his fame, cost physics decades of progress. But the question didn't go away entirely. It couldn't, because the universe doesn't care about scientific politics. Stars above the Chandrasekhar limit exist. They die, and when they die, something has to happen to them. In 1939, two papers appeared that pushed the story forward, and they came from very different directions. The first was by Robert Oppenheimer. Yes, that Oppenheimer, the same man who would later lead the Manhattan Project, working with a graduate student named George Volkoff. They asked a natural follow-up question. Okay, if a star is too massive to become a white dwarf, could it become something even denser? By the late 1930s, physicists knew about neutrons, particles with no electric charge, packed into the atomic nucleus. What if a collapsing star got so dense that the electrons and protons were squeezed together to form neutrons? You'd get a star made almost entirely of neutrons, a neutron star. And neutron degeneracy pressure, similar to electron degeneracy pressure but much stronger, might be able to halt the collapse. Oppenheimer and Volkoff worked out the math, and they found that yes, neutron stars could exist, but they had their own mass limit. Above roughly 3 solar masses, the exact number is still debated, but somewhere in that neighborhood, even neutron degeneracy pressure fails. The neutrons can't hold up the star. Gravity wins again. So now you've got 2 walls, and both of them have been breached. White dwarfs can't support more than 1.4 solar masses. Neutron stars can't support more than about 3 solar masses. And there are plenty of stars out there much more massive than that. So what happens to them? Oppenheimer, working with another student named Hartland Snyder, published a second paper in 1939 that addressed exactly this question, and their answer was stark. They showed, using general relativity, that a sufficiently massive star that has exhausted its fuel will collapse completely, not to a white dwarf, not to a neutron star, all the way down. The matter falls inward. The star shrinks past its own Schwarzschild radius, and from the perspective of a distant observer, it appears to freeze at the event horizon, the light from its surface getting dimmer and dimmer, redder and redder, stretched out by the warping of space-time itself, until it effectively vanishes from view. But the matter itself, from its own perspective, keeps falling. It crosses the horizon and continues inward toward a point of infinite density at the center. Oppenheimer and Snyder had described, in rigorous mathematical terms, the formation of what we would now call a black hole. They'd connected Schwarzschild's abstract geometry to a real physical process. The death of a massive star. The math was clean, the logic was sound, and almost nobody paid attention. Part of the reason was timing. The paper was published on September 1st, 1939, the same day Nazi Germany invaded Poland. The world had other things on its mind. And within a few years, Oppenheimer himself would be consumed by the Manhattan Project, turning his formidable intellect toward a very different kind of physics. The question of gravitational collapse was set aside. Again, not because it was answered, but because history intervened. And so, for nearly 2 decades, from the early 1940s through the late 1950s, the idea of complete gravitational collapse, of a star falling through its own event horizon and forming something from which nothing can escape, existed mostly as a mathematical curiosity. A few theorists thought about it. Most didn't. Einstein himself never accepted it, right up until his death in 1955. He published a paper in 1939, the same year as Oppenheimer's, arguing that the Schwarzschild singularity could not be realized in nature. He was wrong about that, but again, when Einstein says something can't happen, people tend to listen. It's a strange period in the history of physics. The theoretical groundwork for black holes was essentially complete by 1939. The key ideas were all there: the Schwarzschild radius, the Chandrasekhar limit, the Oppenheimer-Snyder collapse solution. All the pieces were on the table, but nobody had assembled them into a coherent picture, and nobody had given the thing a name, and most physicists either didn't know about the work or didn't believe it mattered. The concept was floating in a kind of intellectual limbo, waiting for someone to take it seriously. That would start to change in the late 1950s and early 1960s, when a new generation of physicists, people who hadn't been shaped by the war, who were willing to take general relativity seriously as a tool for understanding real astrophysical objects, began to revisit the problem. And the person who would do more than anyone else to drag black holes out of the realm of mathematical abstraction and into the realm of physical reality was a quiet, determined New Zealander working at Princeton, a man named Roy Kerr. No, wait. Let me back up just slightly, because before we get to Kerr, we need to talk about the person who set the stage for everything that followed. His name was John Archibald Wheeler, and he was one of the most important physicists of the 20th century, even though his name isn't nearly as well known as it should be. Wheeler had worked on the Manhattan Project, he'd collaborated with Niels Bohr on nuclear fission theory, and by the mid-1950s, he was a senior figure at Princeton, the same Princeton where Einstein had spent his final years. And Wheeler did something that sounds simple, but was actually radical for the time. He decided that general relativity deserved to be taken seriously again. See, here's what had happened. After Einstein published General Relativity in 1915, it had this brief golden period where people like Schwarzschild and Eddington were working on it, testing it, pushing it forward. But then, for a couple of decades, it kind of fell out of fashion. Quantum mechanics was the exciting new thing. Nuclear physics was where the action was. General relativity was seen as this beautiful but somewhat impractical theory. Elegant mathematics, sure, but what could you actually do with it? It didn't seem to connect to the kinds of problems physicists were working on day to day. There's a famous phrase that people used to describe general relativity during this period. They called it a low water mark, a backwater of physics. Hardly anyone was working on it. The few who did were often mathematicians rather than physicists, and they were treated as slightly eccentric. Wheeler changed that. Starting in the late 1950s, he began building a research group at Princeton focused on what he called geometrodynamics, the dynamics of geometry itself, the idea that space-time isn't just a passive stage where physics happens but an active, dynamic participant. And he attracted brilliant young people to work on these problems. He was one of those rare mentors who could see talent, nurture it, and point it at exactly the right question at exactly the right time. His students and collaborators would go on to reshape our understanding of gravity, space-time, and yes, black holes. In fact, it was Wheeler himself who popularized the term black hole. He didn't coin it. The phrase had been used informally before, and there's some debate about who said it first. But Wheeler started using it consistently in lectures and papers around 1967, and it stuck. Before that, people were calling these objects frozen stars, or collapsed stars, or Schwarzschild singularities, none of which exactly rolls off the tongue. Black hole was vivid, memorable, slightly ominous. It captured the public imagination in a way that gravitationally completely collapsed object never could. But I'm getting slightly ahead of myself. Let's go back to the late 1950s and the specific problem that needed solving. Remember, the Oppenheimer-Snyder paper from 1939 had shown that a perfectly spherical, non-rotating, pressure-free ball of matter would collapse through its Schwarzschild radius and form a singularity. But that's an incredibly idealized scenario. Real stars aren't perfectly spherical. They rotate. They have lumps and asymmetries and magnetic fields and all kinds of messy complications. And many physicists, including some very smart ones, believed that these real-world imperfections would prevent true collapse from ever happening. The argument went something like this. As a star collapses, any tiny asymmetry would get amplified, and the infalling matter would miss the center, swirl around, and bounce back out. The singularity was just an artifact of assuming perfect symmetry. Take away the symmetry, and the whole thing falls apart. This was a reasonable objection. It wasn't crazy, and it gave people a comfortable reason to ignore the Oppenheimer-Snyder result. But it was wrong, and proving it was wrong would require one of the most elegant pieces of mathematical physics of the 20th century. Enter Roger Penrose. In 1965, Penrose, a British mathematician working at Birkbeck College in London, published a paper that changed everything. It was short, just a few pages, and it introduced a concept called a trapped surface. Here's the idea, and it's worth slowing down for because it's genuinely beautiful. Imagine you're standing in ordinary flat space, and you emit a flash of light. That light spreads outward in an expanding sphere. The sphere gets bigger and bigger as the light moves away from you. Now, imagine you're inside a region of space-time that's so intensely curved by gravity that even the outgoing light, the light you aimed directly away from the center, is actually being focused inward. Both the ingoing and the outgoing light rays are converging. The sphere of light, instead of expanding, is shrinking. That's a trapped surface. And Penrose proved, using very general topological arguments that didn't depend on symmetry at all, that once a trapped surface forms, a singularity is inevitable. It doesn't matter if the collapse is lumpy, or asymmetric, or rotating. It doesn't matter what the matter is made of. Once you have a trapped surface, the mathematics of general relativity guarantees that something goes to infinite density. Game over. Think about what that means. Penrose wasn't solving a specific equation for a specific star. He was proving a theorem, a general statement that applies to any collapsing object in any configuration, as long as certain very reasonable conditions are met. He showed that singularities aren't artifacts of oversimplification. They're features of the theory itself. If general relativity is correct, then singularities are real, and black holes are unavoidable consequences of sufficient gravitational collapse. This was the paper that earned Penrose a share of the 2020 Nobel Prize in Physics, more than half a century after he published it. And it's worth noting that Penrose's work built on ideas that Wheeler's group had been developing. The whole intellectual ecosystem that Wheeler had cultivated at Princeton was part of what made this breakthrough possible. Now, right around the same time, and this is where our New Zealander finally enters the story properly, a mathematician named Roy Kerr was working at the University of Texas at Austin. And in 1963, 2 years before Penrose's singularity theorem, Kerr found something that people had been looking for since 1916. He found the exact solution to Einstein's field equations for a rotating black hole. Let me explain why this matters so much. The Schwarzschild solution from 1916 describes a black hole that isn't rotating and has no electric charge. It's the simplest possible black hole, just mass, nothing else. And it's incredibly useful as a starting point. But here's the thing. Every star in the universe rotates, every single one. So when a real star collapses to form a black hole, the resulting object is going to be spinning. And a spinning black hole is a fundamentally different beast from a non-spinning one. People had been trying to find the rotating solution for nearly 50 years, and nobody could do it. The equations are brutally difficult. You're not looking for a spherically symmetric solution anymore. The rotation breaks that symmetry, so you need something more complicated. Dozens of physicists and mathematicians had attempted it and failed. Kerr was born in 1934 in Coorong, a small town on the South Island of New Zealand, population maybe a few hundred. He was a mathematical prodigy, the kind of kid who could see patterns in equations the way some people see patterns in music. He got his master's degree from the University of New Zealand, then went to Cambridge for his PhD, and eventually ended up in Texas. And in 1963, after months of painstaking calculation, he found it. The Kerr metric, the exact solution for a rotating black hole. The solution was stunning, and not just because it was mathematically elegant, though it absolutely was. What made it so remarkable was what it revealed about the geometry of a spinning black hole. A Schwarzschild black hole has a single event horizon, a spherical boundary, the point of no return. The Kerr black hole has two horizons, an outer one and an inner one, nested inside each other like Russian dolls. And outside the outer horizon, there's a region called the ergosphere, a zone where space-time itself is being dragged around by the rotation of the black hole so violently that nothing can stand still, not even light. If you're in the ergosphere, you are being carried along by the rotation of space-time, whether you like it or not, the way a leaf gets caught in a whirlpool. But here's the crucial thing. You're outside the event horizon. You can still escape. You're being dragged, but you're not trapped. And this leads to one of the wildest ideas in all of physics. Penrose, the same Penrose who proved the singularity theorem, showed in 1969 that you could theoretically extract energy from a rotating black hole by exploiting the ergosphere. The idea is called the Penrose process, and it works like this. You send an object into the ergosphere, and you arrange for it to split into two pieces. One piece falls into the black hole. The other piece comes back out, and here's the kicker. It comes back out with more energy than the original object went in with. The black hole loses a tiny bit of its rotational energy in the process. You're essentially mining the spin of the black hole for energy. It's not perpetual motion. The black hole slows down slightly each time you do it, but the amount of energy available is staggering. Up to 29% of a rotating black hole's total mass energy can theoretically be extracted this way. For a black hole with the mass of our sun, that's more energy than our sun will produce in its entire 10 billion year lifetime. Nobody's going to build a Penrose process machine anytime soon, obviously. But the principle matters because it tells us something deep about the nature of black holes. They're not just cosmic garbage disposals that swallow everything and give nothing back. They're dynamic objects with properties, mass, spin, and as we'll get to later, electric charge, and those properties can change. They interact with the universe around them. Now, when Kerr first presented his solution at a conference in Texas in 1963, the first Texas Symposium on Relativistic Astrophysics, actually, the reaction was mixed. Some people immediately recognized how important it was. Chandrasekhar, who was there, reportedly called it the most important exact solution to Einstein's equations since Schwarzschild's original one. But others didn't fully grasp what they were looking at. The story goes that when Kerr finished his talk, which was only about 10 minutes long, the audience was somewhat muted. Part of the problem was that the conference was dominated by astrophysicists who were focused on a different mystery. Quasars, these incredibly bright objects that had just been discovered at cosmological distances, and many of them weren't equipped to appreciate the mathematical significance of what Kerr had done. There's an almost painful irony here, because as it would turn out, the Kerr solution would eventually be central to explaining how quasars work. But we'll get to that. The other thing that makes the Kerr solution so remarkable is a result that came later, proved by the combined work of several physicists, including Werner Israel, Brandon Carter, David Robinson, and Stephen Hawking over the course of the late 1960s and 1970s. It's called the no-hair theorem, and it says something almost unbelievable. A black hole, no matter how it formed, no matter how complicated the star was that collapsed, no matter what it was made of, no matter what its magnetic field looked like or what its chemical composition was, a black hole is completely described by just 3 numbers: mass, spin, electric charge. That's it. 3 numbers, and you know everything there is to know about the black hole's external gravitational field. Think about how extraordinary that is. A star is one of the most complex objects in the universe. It has layers and convection zones and magnetic fields and chemical gradients and turbulence and nuclear reactions and 100 other things going on. But once it collapses into a black hole, all of that complexity is erased. All that information is gone, or at least it's hidden behind the event horizon where it can never influence the outside universe again. What's left is the simplest macroscopic object in the universe. Wheeler had a wonderful way of putting it. He said, "Black holes have no hair," meaning they have no distinguishing features, no individual characteristics beyond those 3 numbers. A black hole made from a collapsed star, and a black hole made from compressed peanut butter. If they have the same mass, spin, and charge, they are identical. Absolutely, perfectly identical. There is no measurement you could make from outside that would tell them apart. And in practice, astrophysical black holes probably have negligible electric charge, because any charged black hole would quickly attract opposite charges from the surrounding plasma and neutralize itself. So really, a real black hole in nature is described by just 2 numbers, mass and spin. That's the Kerr solution. That's all you need. This simplicity is beautiful, but it also creates a deep puzzle. one of the deepest in all of physics, actually, and one that people are still arguing about today. It's called the information paradox, and it connects to something that a young physicist in a wheelchair at Cambridge was just beginning to think about in the early 1970s. His name was Stephen Hawking, and what he was about to discover would change everything we thought we knew about what a black hole actually is. By the early 1970s, Stephen Hawking was already well into his struggle with motor neuron disease. He'd been diagnosed in 1963 at 21, and doctors had given him maybe 2 years to live. But here he was, nearly a decade later, still working, still thinking, still pushing deeper into the mathematics of curved spacetime than almost anyone alive. His body was failing. He needed a wheelchair. His speech was becoming harder to understand. But his mind was doing some of the most extraordinary work in 20th century physics. And the thing that caught his attention, the thing that would lead to his most famous discovery, started with an argument about the area of a black hole's event horizon. See, Hawking had been thinking about what happens when black holes interact with things. When matter falls into a black hole, the black hole's mass increases and its event horizon gets bigger. That makes sense, right? More mass, larger Schwarzschild radius, bigger horizon. But Hawking noticed something deeper. He proved mathematically that the total area of all event horizons in any process can never decrease. You can merge two black holes together, and the area of the resulting black hole will be at least as large as the sum of the two original areas. Actually, it'll be larger. You can throw matter in, and the area grows, but you can never make it shrink. He published this result in 1971, and it's called the area theorem. And if that reminds you of something from thermodynamics, you're in very good company, because it reminded a lot of people of something from thermodynamics. There's this thing called the second law of thermodynamics, which says that the total entropy of a closed system can never decrease. Entropy, roughly speaking, is a measure of disorder, or more precisely, a measure of how many microscopic arrangements are consistent with the macroscopic state you observe. And here was Hawking saying the area of a black hole's horizon can never decrease. The parallel is almost eerie. Entropy always goes up. Horizon area always goes up. Could they be related? A graduate student at Princeton named Jacob Bekenstein thought so. Bekenstein was working with John Wheeler, the same Wheeler who'd coined black hole, the same Wheeler who'd trained a generation of relativists. And in 1972 and 1973, Bekenstein proposed something radical. He said the area of a black hole's event horizon isn't just analogous to entropy. It actually is entropy. A black hole has entropy, and that entropy is proportional to the area of its horizon. Now, think about why this matters. Remember that puzzle we were just talking about, the no-hair theorem, the idea that a black hole is described by just mass and spin? If that's true, then when a star collapses into a black hole, all the information about what that star was made of, all its complexity, all its entropy, seems to just vanish. And that violates the second law of thermodynamics. You can't just destroy entropy. You can't take a high-entropy system like a star and turn it into a zero-entropy system like a featureless black hole. That would be like unscrambling an egg, but worse. Bekenstein's proposal solved this. He said the entropy didn't disappear. It got transferred to the black hole itself, encoded somehow in the area of the event horizon. The black hole isn't a zero-entropy object at all. It's actually an incredibly high-entropy object. In fact, for a given region of space, a black hole represents the maximum possible entropy you can fit inside that region. That's a wild claim. It means a black hole is the most disordered thing that can exist in a given volume, which is strange because from the outside, it looks like the simplest thing imaginable, just mass and spin. But the entropy is there, hidden in the horizon. Hawking initially didn't like this idea. And here's why. If a black hole has entropy, then by the laws of thermodynamics, it must also have a temperature. And if it has a temperature, it must radiate. Everything with a temperature above absolute zero emits thermal radiation. Your body does it. A warm cup of coffee does it. A star does it. So if a black hole has a temperature, it should glow. But black holes are supposed to be black. Nothing escapes from inside the event horizon. That's the whole point. So Hawking set out to prove Bekenstein wrong. And here's where one of the most beautiful accidents in theoretical physics happens. Hawking tried to disprove Bekenstein, and instead, he proved him right, and discovered something even more astonishing in the process. What Hawking did in 1974 was apply quantum mechanics to the region just outside a black hole's event horizon. Now, this is a subtle and genuinely difficult piece of physics, so let me try to walk you through the basic idea without getting lost in the mathematics. In quantum field theory, the framework that combines quantum mechanics with special relativity, empty space isn't really empty. The vacuum is a seething, buzzing sea of virtual particle pairs that are constantly popping into existence and annihilating each other. An electron and a positron appear out of nothing, exist for an unimaginably brief instant, and then collide and disappear again. This happens everywhere, all the time. Normally, these virtual pairs are completely unobservable. They're a bookkeeping feature of the theory, a way of accounting for quantum fluctuations in the fields. But near the event horizon of a black hole, something strange happens. Imagine a virtual pair appearing right at the edge of the horizon. One particle forms just outside, and the other forms just inside. Normally, they'd find each other and annihilate. But the one that formed inside the horizon is trapped. It can't get back out. It falls inward, and the one that formed outside is suddenly real. It's no longer virtual. It has no partner to annihilate with, so it flies away into space as a genuine, detectable particle. And here's the kicker. The energy for this particle has to come from somewhere, and it comes from the black hole itself. The black hole loses a tiny bit of mass in the process. From far away, it looks like the black hole is emitting radiation, glowing very faintly, like an object with a temperature. This is Hawking radiation. And it was a bombshell. Now, I should be honest with you. The virtual particle pair picture I just described is a simplification. It's the way Hawking himself sometimes explained it to popular audiences, and it captures the essential weirdness, but the actual calculation is more involved. What Hawking really showed is that the quantum vacuum state, as defined by an observer falling into the black hole, is different from the quantum vacuum state as defined by an observer far away. What looks like empty space to the infalling observer looks like a thermal bath of particles to the distant observer. This is related to something called the Unruh effect, discovered around the same time by William Unruh, which shows that even an accelerating observer in flat space-time perceives the vacuum as filled with thermal radiation. The event horizon of a black hole creates a similar effect, but permanently and for everyone outside. The temperature of this radiation is inversely proportional to the black hole's mass. And for any black hole we'd actually expect to find in nature, one formed from a collapsed star, say, with a mass of several suns, The temperature is absurdly low. We're talking about something like 60 billionths of a Kelvin above absolute zero. That's far, far colder than the cosmic microwave background radiation that fills all of space, which sits at about 2.7 Kelvin. So in practice, real astrophysical black holes are absorbing far more energy from the cosmic background than they're emitting through Hawking radiation. They're actually growing, not shrinking. The effect is unmeasurably tiny for any black hole we could observe with current technology. But here's what matters. In principle, a black hole radiates. It has a temperature. It has entropy. It's a thermodynamic object. And if you could somehow isolate a black hole from all external radiation and just let it sit there, it would slowly, incredibly slowly, evaporate. It would lose mass, and as it lost mass, its temperature would rise, because temperature is inversely proportional to mass, and it would radiate faster, and lose mass faster, and get hotter, and radiate even faster, in a runaway process that ends with the black hole shrinking down to nothing and disappearing in a final burst of radiation. For a stellar mass black hole, this process would take something like 10 to the power of 67 years. That's a 1 followed by 67 zeros. The current age of the universe is only about 10 to the power of 10 years. So we're talking about timescales that are almost incomprehensibly long. But it's finite. Given enough time, every black hole in the universe will eventually evaporate. Hawking published this result in a paper in the journal Nature in 1974, titled Black Hole Explosions? With a question mark, because even he seemed a little startled by what he'd found. And the reaction from the physics community was a mixture of awe and deep unease. Awe, because it was brilliant. It was the first concrete result that combined general relativity with quantum mechanics and got a definite, physical prediction. It showed that these two great pillars of modern physics, which had stubbornly refused to merge into a single theory, could at least be made to talk to each other in the vicinity of a black hole. That was thrilling. But the unease came from the implications. Because Hawking radiation creates a problem. A really, really deep problem. And it's precisely that information paradox we've been circling around. Here's the issue. When a black hole evaporates, it emits thermal radiation. Thermal radiation is random. It's characterized only by a temperature. It carries no information about what fell into the black hole in the first place. So imagine you throw a book into a black hole. The black hole's mass increases slightly, its horizon area increases, and all the information in that book, every word, every letter, is now behind the event horizon. Then, over an unimaginably long time, the black hole evaporates away completely through Hawking radiation. It's gone, and the radiation it emitted was purely thermal, purely random. So where did the information in the book go? It didn't come out in the radiation, because the radiation is featureless. It can't still be inside the black hole, because the black hole no longer exists. It seems like the information was simply destroyed, erased from the universe, and that violates one of the deepest principles of quantum mechanics, the principle of unitarity, which says that information is always conserved. Quantum mechanics is, at its core, a deterministic theory in one specific sense. If you know the complete quantum state of a system at one time, you can in principle calculate it at any other time, past or future. Information is never lost. But Hawking's calculations seem to show that black holes destroy information, and that means either quantum mechanics is wrong, or general relativity is wrong, or there's something about the evaporation process that we don't yet understand. Hawking himself, for decades, argued that information really is destroyed. He was willing to modify quantum mechanics to accommodate this, and this put him on one side of what became one of the great debates in theoretical physics, a debate that pulled in some of the brightest minds of the late 20th century. On the other side were people like Leonard Susskind at Stanford and Gerard at Hooft in the Netherlands, both of whom insisted that information must be preserved, that quantum mechanics cannot be violated, and that somehow, the information comes back out in the Hawking radiation, encoded in subtle correlations that Hawking's original calculation was too crude to capture. This argument went on for decades. Susskind has written about it beautifully. He called it the Black Hole War, and he meant it. It was personal, it was intense, and it touched on the most fundamental questions about the nature of reality. And it led to some of the most surprising ideas in modern physics, ideas that sound almost too strange to be true. One of them is called the holographic principle, and it starts with a deceptively simple question about where information actually lives. Not inside a volume of space, the way you'd intuitively expect, but on its boundary, on its surface. Think about that for a second. All the information contained in a room, every atom, every particle, every quantum state of everything inside that three-dimensional volume, could, in principle, be fully described by data encoded on the two-dimensional walls of that room. Not a summary, not a compressed version, the complete description. Everything happening inside the volume is equivalent to something written on the boundary. That's the holographic principle, and it's one of the most disorienting ideas in all of physics. The name comes from ordinary holograms, those shimmery images you've probably seen on credit cards or novelty stickers. A hologram is a two-dimensional surface that encodes three-dimensional information. You tilt it, and the image seems to have depth, seems to rotate, because the interference pattern on that flat surface contains enough data to reconstruct the full three-dimensional scene. The holographic principle says the universe might work the same way, at the deepest level, that the three-dimensional world we experience could be a kind of projection of information living on a distant two-dimensional surface, which sounds absolutely wild. It sounds like science fiction. But the reasoning that leads there is surprisingly grounded, and it starts right back with Bekenstein and those black holes. Remember what Bekenstein figured out in the early 70s, that the entropy of a black hole is proportional to the area of its event horizon, not its volume. That was strange enough on its own, because entropy is supposed to count the number of microscopic ways something can be arranged, and you'd expect that number to scale with volume. A bigger box has more room for stuff, more possible configurations, more entropy. But black holes don't work that way. Their entropy scales with surface area. And Bekenstein's formula, refined by Hawking, gives a precise number. The entropy is 1/4 of the horizon area, measured in Planck units. 1/4. That fraction, 1/4, keeps showing up in black hole physics like a fingerprint, and nobody fully understands why it's specifically 1/4 rather than some other number. But the area scaling, that part has deep implications. Here's why. A black hole is the most entropic object that can fit in a given region of space. You cannot pack more entropy into a sphere than a black hole of that size already contains. If you tried, if you kept cramming more and more stuff into a region, eventually you'd form a black hole, and the entropy would be exactly the Bekenstein-Hawking value, proportional to the area of the resulting horizon. This means there's a maximum amount of information that any region of space can hold, and that maximum is determined not by the volume of the region, but by the area of its boundary. Volume doesn't matter. The surface is what sets the limit. Gerard 't Hooft was one of the first to take this seriously as a general principle, not just a quirk of black holes. In 1993, he proposed that any consistent theory of quantum gravity must be holographic, that the physics of any volume of space must be describable by a theory living on the boundary of that volume, with no more than 1 degree of freedom per Planck area on that boundary. A Planck area is unimaginably tiny, about 10 to the minus 66 square centimeters, so you can fit an enormous amount of information on any macroscopic surface. But the point is that it's finite, and it's set by the area, not the volume. Susskind picked this up and developed it further, and by the mid-90s, the holographic principle was becoming one of the central ideas in the quest for quantum gravity. Now, you might be thinking, okay, that's a beautiful mathematical idea, but is there any concrete realization of it? Is there a specific example where you can actually show that a theory in some volume of space is exactly equivalent to a theory on its boundary? And the answer is yes. And it came in 1997 from a young physicist named Juan Maldacena, who was then at Harvard. What Maldacena found is often called the most important theoretical result in physics in the last 30 years, and it goes by the name ADS/CFT correspondence, which is a mouthful, so let's unpack it slowly. ADS stands for anti-de Sitter space, which is a particular geometry of spacetime. Imagine a universe that has a negative cosmological constant. Instead of expanding the way our universe does, it has a kind of natural tendency to curve inward, like the inside of a saddle shape extended into all dimensions. It's not our universe. Our universe appears to have a positive cosmological constant, which is what drives the accelerating expansion we observe. But anti-de Sitter space is a perfectly valid solution to Einstein's equations, and it turns out to be an incredibly useful theoretical laboratory. CFT stands for conformal field theory, which is a type of quantum field theory. Think of it as a quantum theory of particles and forces, but one that has a special kind of symmetry called conformal symmetry, which roughly means it looks the same at all scales. What Maldacena showed is that a theory of quantum gravity in the interior of anti-de Sitter space, a full theory, including gravity, strings, black holes, everything, is exactly equivalent to a conformal field theory living on the boundary of that space, which has 1 fewer dimension and no gravity at all. The bulk has gravity. The boundary doesn't. They're the same theory, written in 2 completely different languages. Every question you could ask about quantum gravity in the interior can be translated into a question about ordinary quantum physics on the boundary, and vice versa. It's a dictionary between 2 seemingly unrelated descriptions of reality. And here's what's really clever about this for the black hole information problem. On the boundary, there's no gravity, and the theory is a perfectly well-behaved quantum field theory. Quantum field theories are unitary. They conserve information. Always. No exceptions. So, if the boundary theory conserves information, and the boundary theory is exactly equivalent to the bulk theory that includes black holes, then black holes must also conserve information. The information paradox, in the context of ADS/CFT, is resolved by fiat almost, the holographic dual guarantees that information gets out. The question becomes not whether information escapes, but how. This was a huge moment. It didn't give you a step-by-step mechanism for how information leaks out of a black hole through Hawking radiation. It didn't tell you exactly what happens to the quantum state of a book that falls past the horizon. But it provided extraordinarily strong evidence that Susskind and 't Hooft were right and Hawking was wrong. Information is preserved. The framework essentially says, look, we have this exact mathematical equivalence, and on one side of the equivalence information is obviously conserved, so it must be conserved on the other side too, even if we can't yet see how. Hawking himself eventually conceded. In 2004, at a conference in Dublin, he announced that he had changed his mind. That information is not destroyed by black holes after all. He'd made a bet with John Preskill of Caltech back in 1997, wagering that information was truly lost, and in Dublin, he conceded the bet and gave Preskill a baseball encyclopedia, a symbol of information being preserved. Susskind, who had spent decades on the other side of this argument, later wrote that Hawking's concession was gracious but also somewhat anticlimactic, because by 2004 the evidence from ADS/CFT had already convinced most of the theoretical physics community. The war, in a sense, had already been won. But here's the thing. Knowing that information gets out is very different from understanding how it gets out. And the how question has driven some of the most creative and bizarre ideas in 21st century physics. One of them involves a concept called complementarity, which Susskind and his collaborators developed in the early 90s. The idea is this. If you're falling into a black hole, you experience one version of reality. You pass smoothly through the horizon. Nothing special happens at the surface, and you eventually encounter extreme tidal forces deeper inside. But if you're watching from the outside, you see a completely different story. You see the infalling person slow down, redshift, and smear across the horizon, with their information gradually being re-emitted in the Hawking radiation. Both descriptions are valid. Both are complete. But no single observer ever sees a contradiction, because no single observer can be both inside and outside the black hole simultaneously. It's like quantum mechanics' own version of diplomatic immunity. The two stories never meet, so they never conflict. This was a satisfying resolution for a while. It respected both general relativity, which says the horizon is nothing special for an infalling observer, and quantum mechanics, which demands that information be accessible to outside observers. But in 2012, a group of physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, often called AMPS after their initials, published a paper that blew complementarity apart, or at least revealed a deep tension within it. Their argument, known as the firewall paradox, goes something like this. If information really does come out in the Hawking radiation, then the late-time radiation, the Hawking particles emitted after the black hole has already radiated away more than half its initial entropy, must be entangled with the early-time radiation that left long ago. That's how the information gets out, through quantum entanglement between early and late radiation. But quantum mechanics also says that each Hawking particle, at the moment it's created near the horizon, must be entangled with its partner particle that falls into the black hole. And here's the problem. A fundamental result in quantum mechanics called the monogamy of entanglement says that a quantum system cannot be maximally entangled with two different systems at the same time. The late Hawking particle can't be fully entangled with both the early radiation and its infalling partner. Something has to give. AMPS argued that what gives is the smooth horizon. If you break the entanglement between the outgoing Hawking particle and its infalling partner, which you must do to preserve information, then the horizon is no longer a calm, unremarkable surface. Instead, it becomes a searing wall of high-energy quanta, a firewall. Anyone falling into an old enough black hole wouldn't glide peacefully through the horizon. They'd be incinerated. which directly contradicts general relativity's equivalence principle, one of the most foundational ideas in all of physics. The principle that says a freely falling observer should notice nothing special about the horizon. So now you've got a three-way standoff. You can preserve information and keep quantum mechanics happy, but you destroy the smooth horizon and violate general relativity. You can keep the smooth horizon, but then information is lost and quantum mechanics is violated. Or you can try to find some subtle escape route that preserves all three: unitarity, the equivalence principle, and the structure of quantum entanglement. And this is roughly where the field stands today, a decade plus later, still arguing, still searching, still turning the problem over and over like a puzzle box that won't quite open. Some of the proposed resolutions are genuinely mind-bending. One idea, championed by Maldacena and Susskind in 2013, is called ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, and EPR refers to Einstein-Podolsky-Rosen entanglement, the spooky action at a distance that Einstein himself was so uncomfortable with. The conjecture says that every pair of entangled particles is connected by a tiny, non-traversable wormhole. Entanglement and wormholes are the same thing, seen from different angles. If that's true, then the entanglement between Hawking radiation and the black hole interior isn't just an abstract quantum correlation. It's a physical geometric connection, a bridge in space-time itself. And maybe, just maybe, that bridge is how information gets from the inside to the outside without anything dramatic happening at the horizon. It's speculative, it's unproven, but it's the kind of idea that makes you lie awake at night staring at the ceiling, wondering whether the fabric of space-time is literally woven out of quantum entanglement, whether space itself emerges from the connections between quantum systems rather than being a stage on which quantum systems perform. And that idea, that space-time might be emergent rather than fundamental, has become one of the hottest topics in theoretical physics. It connects to something called quantum error correction, of all things, the same mathematical framework that people are developing to build quantum computers. It turns out that the way the holographic principle encodes bulk information on a boundary looks remarkably like a quantum error correcting code, where the information is distributed redundantly, so that even if you lose access to part of the boundary, you can still reconstruct what's happening in the interior, which means the universe might literally be structured like a quantum computer's memory, protecting information through redundancy and entanglement. But we should step back from the theoretical stratosphere for a moment, because while all of this was happening, while theorists were arguing about firewalls and holography and the fate of information, observational astronomers were doing something extraordinary. They were finding black holes, real ones, not on chalkboards or in equations, but out there in the actual universe, behaving in ways that could be measured, photographed, and listened to. And that story, the story of actually detecting black holes, of turning them from mathematical abstractions into confirmed astrophysical objects, is one of the great adventure stories in modern science. It starts, in a way, with X-rays. Back in the early 1960s, astronomers were just beginning to launch instruments above Earth's atmosphere to look at the sky in wavelengths that don't penetrate our blanket of air. And in 1964, a source of powerful X-ray emission was identified in the constellation Cygnus. They called it Cygnus X1. It was bright, it flickered rapidly, and it was clearly something compact and energetic. But what? A neutron star, maybe. Those were known to exist by then. Incredibly dense remnants of collapsed stars packing more mass than the sun into a ball the size of a city. Neutron stars could produce X-rays if they were pulling matter off a companion star, heating that matter to millions of degrees as it spiraled inward. So that was the safe bet. But Cygnus X1 had a problem. As astronomers studied it through the late 1960s and into the 1970s, they pinned down the mass of the compact object by watching how it and its companion star orbited each other. You can do this with spectroscopy, measuring the Doppler shifts in the light from the visible star as it swings toward you and away from you in its orbit. It's the same principle as a siren changing pitch as an ambulance passes. And when they worked out the orbital mechanics, the compact object in Cygnus X1 came in at something like 6 to 10 times the mass of the Sun. That's way too heavy to be a neutron star. There's a limit, the Tolman-Oppenheimer-Volkoff limit, above which even neutron degeneracy pressure can't hold a star up against gravity. That limit is somewhere around 2 to 3 solar masses, depending on the details of nuclear physics. Cygnus X1 blew past it. So what do you have when you've got something that massive, that compact? That's not a neutron star. You have a black hole. Or at least, that's what the evidence strongly suggested. And this is where one of the most famous scientific bets in history comes in. Stephen Hawking, despite having done more than almost anyone to develop the theory of black holes, bet Kip Thorne in 1974 that Cygnus X1 was not actually a black hole. It sounds contradictory, right? But Hawking later explained that it was a kind of insurance policy. If black holes turned out not to exist, at least he'd win the bet, which would be some consolation for all his theoretical work being wrong. Thorne took the other side. The stakes were a subscription to Penthouse magazine for Thorne if he won, and Private Eye magazine for Hawking if he did. By 1990, the evidence had become so overwhelming that Hawking conceded. Cygnus X1 was, almost certainly, a black hole. But almost certainly is doing some work in that sentence. The thing about black holes is that you can't see them directly. That's kind of the whole point. What you see is their effect on everything around them. You see the X-rays from superheated gas. You see the orbital dance of companion stars. You see jets of material being flung outward at nearly the speed of light from the regions just outside the event horizon. All of this is circumstantial evidence, and for decades, some physicists, a shrinking minority but a vocal one, held out the possibility that these objects might be something else, something exotic we hadn't thought of yet. So the quest became, can we get more direct evidence? Can we actually see the shadow of a black hole, the silhouette of an event horizon against the glow of infalling matter? And can we detect the space-time ripples that black holes create when they collide? Let's take those in order, because they're both incredible stories. Gravitational waves first. Einstein predicted them in 1916, just months after publishing General Relativity. The idea is beautifully simple in concept. If mass curves space-time, then accelerating masses should create ripples in that curvature, the way shaking your hand in a bathtub creates waves on the water's surface. These ripples would propagate outward at the speed of light, stretching and squeezing space itself as they pass. But Einstein also calculated how strong these waves would be, and the answer was unimaginably faint. Even violent cosmic events, supernovae, colliding stars, would produce gravitational waves that, by the time they reached Earth, would stretch a kilometer-long ruler by less than 1,000th of the diameter of a proton. Einstein himself doubted they could ever be detected. He actually went back and forth on whether they were even real physical phenomena or just mathematical artifacts of his equations. There was a whole controversy in the 1930s and 1940s about this, and it wasn't fully settled until the 1950s and 1960s when theorists like Hermann Bondi showed convincingly that gravitational waves carry real energy. But detecting them? That seemed hopeless for most of the 20th century. A physicist named Joseph Weber built the first gravitational wave detectors in the 1960s. Large aluminum cylinders that were supposed to vibrate like tuning forks when a wave passed through. Weber actually claimed to detect signals in 1969, which caused enormous excitement. But other groups built similar detectors and couldn't reproduce his results. It was a painful episode. Weber spent the rest of his career defending his claims, increasingly isolated. He died in 2000 without the vindication he sought, but his work inspired a generation of physicists to take the detection problem seriously. The approach that ultimately worked was laser interferometry. The idea is this: you build two long arms at right angles to each other, like a giant L. You send laser beams down both arms, bounce them off mirrors at the far ends, and bring them back together. If the arms are exactly the same length, the light waves recombine in a specific pattern. But if a gravitational wave passes through, it stretches one arm and compresses the other. By that absurdly tiny amount, less than a proton's width. And the recombining light shifts just slightly. You can measure that shift. The project that made this real is called LIGO, the Laser Interferometer Gravitational Wave Observatory. It was the brainchild of Rainer Weiss at MIT, who worked out the basic concept in the early 1970s, and Kip Thorne and Ronald Drever at Caltech, who pushed it forward through the 1980s and 1990s. Getting it funded was a saga in itself. LIGO was the most expensive project the National Science Foundation had ever backed, hundreds of millions of dollars for what many physicists considered a long shot. There were bitter internal disputes, political battles, and years of technical setbacks. Two enormous detectors were built, one in Hanford, Washington, and one in Livingston, Louisiana, each with arms 4 kilometers long. The initial version of LIGO ran from 2002 to 2010 and detected nothing. Which was expected, actually. The initial design was meant to prove the technology worked, not to be sensitive enough for routine detection. Then came Advanced LIGO, a major upgrade that increased sensitivity by about a factor of 10. And here's where the story gets almost too perfect. On September 14, 2015, just 2 days after Advanced LIGO was switched on for its first observing run, before the run had even officially started, while they were still doing engineering tests, both detectors picked up a signal. A very specific signal. A chirp. A rising frequency that swept upward over about 0.2 of a second, then cut off. When the team analyzed it, the signal matched, with extraordinary precision, the prediction from general relativity for two black holes spiraling into each other and merging. Two black holes, one about 36 times the mass of the Sun and the other about 29 times, had been circling each other, losing energy to gravitational waves, spiraling closer and closer, moving faster and faster, until they merged into a single black hole of about 62 solar masses. If you do the math, you'll notice that 36 plus 29 is 65, not 62. Those three missing solar masses, 3 times the mass of our Sun, were converted entirely into gravitational wave energy during the final fraction of a second of the merger. 3 solar masses converted to pure energy in less than a second. That's more power output than all the stars in the observable universe combined for that brief instant. Think about that for a moment. Just let it settle. The sheer violence of that event, happening 1.3 billion light-years away, so long ago that multicellular life on Earth had barely gotten started, sent a ripple through the fabric of space-time that expanded outward for over 1 billion years. And when it finally washed over the Earth on a quiet Monday morning in September 2015, it stretched LIGO's 4-kilometer arms by about 4/1000ths of the diameter of a proton, and they measured it. The discovery was announced on February 11, 2016. Weiss, Thorne, and Barry Barish, who had taken over leadership of LIGO in the 1990s and transformed it from a struggling project into a functioning observatory, received the Nobel Prize in Physics in 2017. And since that first detection, LIGO and its European partner Virgo have detected dozens more gravitational wave events, most of them black hole mergers. We've seen black holes of wildly different masses colliding. We've seen neutron stars merging. We've even seen what appear to be black holes swallowing neutron stars. Each detection teaches us something new about how these objects form, how they find each other, and how gravity behaves in the most extreme conditions imaginable. But gravitational waves, as spectacular as they are, give you sound without a picture. You hear the black holes, in a sense. The chirp can literally be converted to audio, and it sounds like a quick rising tone, a cosmic bloop. What you don't get is an image. And humans, we want to see things. We want a picture. Which brings us to the Event Horizon Telescope, and one of the most ambitious observations in the history of astronomy. The idea goes back to the early 2000s, when a number of radio astronomers realized that the supermassive black hole at the center of our galaxy, called Sagittarius A star, or SGRA star for short, that little star is pronounced A star, might be large enough and close enough that its shadow could be resolved with a radio telescope of sufficient resolution. The black hole itself has a mass of about 4 million suns. We know this because astronomers, particularly Andrea Ghez and Reinhard Genzel, spent years tracking individual stars orbiting the galactic center, watching them trace out elliptical paths around an invisible point, moving at thousands of kilometers per second. That work, which earned Ghez and Genzel a share of the 2020 Nobel Prize, gave us the mass and location of the black hole with exquisite precision. But actually, seeing its shadow required a telescope with a resolution equivalent to reading a newspaper in New York from a cafe in Paris. No single telescope on Earth can do that. But here's the trick. If you link together radio telescopes scattered across the globe, all observing the same target at the same time, you can combine their data to create a virtual telescope with an effective diameter equal to the distance between the most widely separated dishes. This technique is called very long baseline interferometry, and it had been used for decades. The Event Horizon Telescope project, led by Shepard Dolaman, took it to its extreme, linking dishes in Hawaii, Arizona, Spain, Chile, Mexico, the South Pole, and other locations to create a virtual telescope the size of the Earth. They observed 2 targets, Sagittarius A star and a much more massive black hole in the galaxy, M87, about 55 million light-years away. M87's black hole is a monster, 6.5 billion solar masses. It's much farther away than SGRA star, but it's also much bigger, so it appears roughly the same angular size on the sky. And on April 10th, 2019, the collaboration released the image. You've probably seen it, even if you don't remember the context. It's a blurry orange ring, brighter on one side than the other, surrounding a dark central shadow. That dark region is the silhouette of the event horizon, or more precisely, the photon sphere just outside it, seen against the glowing accretion disk of superheated plasma swirling around the black hole. The asymmetry, brighter on one side, comes from relativistic beaming. The material moving toward us appears brighter because of Doppler effects, while the material moving away appears dimmer. Everything about the image matched the predictions of general relativity: the size of the shadow, the shape, the brightness profile. All of it consistent with what Einstein's equations said a black hole should look like, calculated by simulations that took into account the bending of light, the rotation of the black hole, and the dynamics of the surrounding plasma. 3 years later, in 2022, the team released an image of Sagittarius A star, our own galaxy's black hole. It was harder to image because SGR A star is much smaller, and the gas around it changes on timescales of minutes, blurring the picture, whereas M87's black hole is so large that its dynamics play out over days and weeks, giving you a more stable target. But they managed it. And again, a glowing ring, a dark shadow. General relativity confirmed in the strong field regime right at the doorstep of an event horizon. So by the early 2020s, the situation had transformed completely from where things stood even a generation earlier. Black holes had gone from controversial theoretical predictions to objects we could hear merging through gravitational waves and photograph through coordinated radio telescopes spanning the planet. We had Nobel Prizes for detecting them, imaging them, and mapping their gravitational influence on nearby stars. The theoretical framework of general relativity had been confirmed in the most extreme environments we could access. And yet, and this is what keeps physicists up at night, in a different way than the kind of staying up you and I are doing right now, the deepest questions remain open. Because all of these observations confirm that black holes behave exactly as general relativity predicts on the outside. The event horizon is where Einstein said it would be. The shadow is the right size and shape. The gravitational waves match the templates. But general relativity is a classical theory. It doesn't know about quantum mechanics. And the questions that Hawking and Bekenstein and Susskind and all the others raised, about information, about entropy, about what happens at the singularity, about whether space-time itself is fundamental, those questions live at the intersection of gravity and quantum mechanics, in a regime that our current observations can't quite reach yet. And that word yet is doing a lot of heavy lifting, because the whole frontier of physics right now, in some sense, is about figuring out how to push into that regime. How do you build a theory that handles gravity and quantum mechanics at the same time, in the places where both of them matter? Which is to say, inside and around black holes. So let's talk about that. Let's talk about what we don't know, and what people are trying to do about it. The core problem, if you strip away all the technical language, is almost embarrassingly simple to state. We have two theories. General relativity describes gravity as the curvature of space-time, and it works spectacularly well for big things: planets, stars, galaxies, the expansion of the universe. Quantum mechanics describes the behavior of particles and forces at tiny scales, and it works spectacularly well for small things: atoms, photons, the interactions that hold your body together. Both theories have been tested to extraordinary precision. Neither one has ever been caught making a wrong prediction within its domain. And they are, in their current forms, fundamentally incompatible. It's not that they disagree on some minor detail. It's that they speak different languages about what reality is. In quantum mechanics, things happen on a fixed stage. Space and time are a backdrop, and particles dance around on that backdrop according to probabilistic rules. In general relativity, there is no fixed stage. Space-time itself is a dynamic thing that bends and warps and responds to the matter and energy within it. So when you try to write down a quantum theory of gravity, when you try to apply quantum rules to space-time itself, you run into conceptual problems that aren't just hard. They're the kind of hard that suggests you're missing something fundamental about how reality works. And black holes are where this incompatibility becomes impossible to ignore. Think about what happens at the singularity. General relativity says that inside a black hole, matter gets compressed to infinite density in zero volume. That's the theory's own prediction, and it's also the theory screaming at you that it's broken. Infinite density isn't a physical thing. It's a sign that your equations have been pushed past their range of validity, like trying to use a road map to navigate the ocean. You need a different map. You need quantum gravity. Or think about the information paradox, which we spent a lot of time with earlier. Hawking radiation seems to destroy information, which quantum mechanics says is impossible. Resolving that paradox requires understanding what's really happening at the event horizon and inside the black hole at a quantum level. Every proposed resolution, complementarity, firewalls, ER equals EPR, quantum error correction in the holographic boundary, all of them are gestures toward a theory of quantum gravity that we don't fully have yet. So, what are the candidates? What are physicists actually working on? The most famous attempt is string theory, and it's worth spending a little time with because it's deeply connected to the black hole story we've been telling. String theory proposes that the fundamental constituents of reality aren't point particles, but tiny, vibrating one-dimensional objects, strings. Different vibration modes of the string correspond to different particles, the way different vibration modes of a guitar string produce different notes. And here's the thing that made string theory so seductive when it was first being developed in the 1970s and 1980s. When you work out the mathematics of these vibrating strings, gravity emerges automatically. You don't have to put it in by hand. One of the vibration modes naturally has the properties of the graviton, the hypothetical quantum particle that would carry the gravitational force. So string theory, almost by accident, seemed to be a quantum theory that included gravity from the start. Now, string theory comes with a lot of baggage. It requires extra dimensions of space, 6 or 7 of them, depending on the version, curled up so small we can't see them. It has an enormous landscape of possible solutions, maybe 10 to the 500th power different possible configurations, and we don't know which one, if any, describes our universe. It has not, as of the mid-2020s, made a single testable prediction that could distinguish it from other approaches. These are legitimate criticisms, and they've fueled decades of sometimes bitter debate within physics. But here's why string theory matters for our story. Remember when we talked about Bekenstein and Hawking figuring out that black holes have entropy, and that the entropy is proportional to the area of the event horizon? That was a stunning result, but it raised an obvious question. Entropy counts microstates. When you say a gas has a certain entropy, you mean there are a certain number of different microscopic arrangements of the gas molecules that all look the same from the outside. So, if a black hole has entropy, there must be microstates, some microscopic quantum description of the black hole that accounts for all those different configurations. But what are they? General relativity gives you a smooth, featureless event horizon. The no-hair theorem says the black hole is completely described by mass, charge, and spin. Where are the microstates hiding? In 1996, Andrew Strominger and Qumran Vafa, working within string theory, managed to count the microstates of a very specific type of black hole, a supersymmetric, extremely charged black hole in 5 dimensions. Not exactly the kind of black hole you'd find in nature. but they could construct it in string theory, count all the different microscopic string configurations that would produce a black hole with that particular mass and charge. And when they did the counting, they got exactly the Bekenstein-Hawking entropy. Exactly. Not approximately, not in the right ballpark. Exactly. That was a huge moment. It was the first time anyone had derived black hole entropy from a microscopic theory. It didn't prove string theory was right about everything, but it showed that string theory could do something no other framework had managed. It could look inside a black hole, in some sense, and count what was there, and get the right answer. It was like finding a key that fit a lock everyone had been staring at for 20 years. Since then, the microstate counting has been extended to other types of black holes, though always in somewhat idealized settings. There's a whole research program sometimes called the fuzzball proposal, led by Samir Mathur and others, which suggests that what we think of as a black hole isn't really a smooth spacetime with a singularity at the center. Instead, it's a complicated quantum object, a fuzzball, where the microstates extend all the way out to where the event horizon would be. In this picture, there is no event horizon in the traditional sense, and there's no singularity. The whole thing is a big, messy quantum state. It's a radical idea, and it's controversial, but it's the kind of radical idea that the information paradox might require. Now, string theory isn't the only game in town. There's another major approach called loop quantum gravity, which takes a very different philosophical starting point. Instead of adding new ingredients like strings and extra dimensions, loop quantum gravity tries to apply quantum mechanics directly to general relativity's own description of spacetime. The result is that spacetime itself becomes quantized. It comes in discrete chunks, like pixels on a screen, but in 3 dimensions. Space is made of tiny grains, each one roughly a Planck length across, about 10 to the minus 35 meters. That's so small that if an atom were the size of the observable universe, a Planck length would be about the size of a tree. In loop quantum gravity, the singularity inside a black hole might be resolved naturally. When matter collapses to very small scales, the discreteness of spacetime kicks in and prevents the density from going to infinity. Instead of a singularity, you might get a Planck star, a region of incredibly dense but finite matter, held up by quantum gravitational effects, the way a neutron star is held up by quantum mechanical effects at a larger scale. Some researchers like Carlo Rovelli and Francesca Vidotto have proposed that this Planck star might eventually bounce, causing the black hole to explode in a burst of energy after an incredibly long time. It's a beautiful idea, though like many quantum gravity proposals, it's very far from being testable with current technology. And then there are other approaches, causal set theory, which proposes that spacetime is fundamentally a discrete set of events connected by causal relationships. There's asymptotic safety, which suggests that gravity might be well behaved at quantum scales after all, if you handle the mathematics carefully enough. There's the whole emergent spacetime program that we touched on earlier, inspired by the holographic principle and ADS/CFT, which suggests that maybe we shouldn't be trying to quantize spacetime at all, because spacetime isn't fundamental. It's something that emerges from a deeper quantum description, like temperature emerges from the motion of molecules. This last idea is particularly fascinating because it turns the whole problem on its head. Instead of asking, how do we fit gravity into quantum mechanics? It asks, how does something that looks like gravity and spacetime arise from purely quantum mechanical ingredients? And black holes, once again, are the key testing ground, because they're where the relationship between quantum information and the geometry of spacetime is most dramatic and most constrained. Here's what's really striking about where things stand right now. Despite all these different approaches, there are certain results that keep showing up across frameworks. The Bekenstein-Hawking entropy formula appears in string theory, in loop quantum gravity, in various semi-classical calculations. The holographic principle, the idea that the information content of a region is bounded by its surface area, not its volume, seems to be robust, appearing in different guises in different approaches. The idea that entanglement and geometry are deeply connected keeps emerging from different starting points. It's as if the different approaches are all catching glimpses of the same underlying structure from different angles, like people feeling different parts of the same elephant in the dark. And this is where the story connects back to something very practical, or at least as practical as fundamental physics gets. Because the quest to understand black holes at the quantum level isn't just about black holes, it's about the nature of space and time themselves. If space-time is emergent, if it's woven from quantum entanglement, then understanding that weaving tells you something profound about the fabric of reality at every scale, not just at the center of a black hole, but right here, right now, in the space between you and the walls of the room you're lying in. There's a wonderful irony in all of this. Black holes started as a mathematical curiosity, an embarrassing prediction that most physicists wanted to ignore. Then they became objects of theoretical fascination. Then they became real, confirmed by observation after observation. And now, they've become the most important laboratory in all of physics. Not a laboratory you can build on Earth, but a theoretical laboratory, a place where you can stress test your ideas about the deepest laws of nature and see which ones survive. And there's one more piece of this story that's worth settling into, because it's happening right now, in the mid-2020s, and it brings together almost everything we've talked about. It's called the Page Curve, and it's named after Don Page, a physicist who's been thinking about black holes and information for decades. Page was actually Stephen Hawking's PhD student at Cambridge in the 1970s, right there at the beginning when Hawking radiation was first being worked out. And Page asked a deceptively simple question. One of those questions that sounds almost too obvious, but turns out to crack open everything. He asked, if a black hole forms, radiates away through Hawking radiation, and eventually disappears completely, what happens to the entanglement between the radiation that's already escaped and the black hole that's still shrinking? Here's why that question matters. When Hawking radiation is produced near the event horizon, each particle that escapes is entangled with a partner that falls into the black hole. Early on, when the black hole is big and is only radiated a little, most of the information, most of the quantum entanglement, is still locked up inside the black hole. The radiation that's escaped so far is highly entangled with the black hole's interior, and if you only looked at the radiation by itself, it would appear almost perfectly random, almost perfectly thermal, just like Hawking originally described. But here's the thing. As the black hole keeps radiating, it's getting smaller. It's losing mass, and at some point, roughly halfway through its evaporation, when it's radiated away about half its original entropy, something has to change. Because if information is truly conserved, if the universe is fundamentally unitary, the way quantum mechanics demands, then the radiation can't keep getting more and more entangled with a black hole that's getting smaller and smaller. At some point, the entanglement between the escaped radiation and the remaining black hole has to start decreasing. The radiation has to start purifying itself, becoming less random, encoding more and more of the information that was originally inside the black hole. Page worked this out in the early 1990s and plotted it as a curve, the entanglement entropy of the radiation as a function of time. It rises during the first half of the evaporation, hits a peak at what's now called the page time, and then falls back down, eventually reaching zero when the black hole has completely evaporated and all the information has been transferred to the radiation. That curve, that rise and fall shape, is the page curve, and it's the signature of unitarity. It's what the entanglement entropy must look like if information is conserved. Hawking's original calculation, by contrast, predicted that the entanglement entropy would just keep rising and rising all the way until the black hole was gone, leaving you with maximally entangled radiation that had nothing left to be entangled with. Which is a contradiction, a paradox, the information paradox expressed in its sharpest mathematical form. So for decades, the challenge was clear. If you believe information is conserved, and by the early 2000s, most physicists did, especially after the successes of ADS/CFT, then you need to reproduce the page curve from a gravitational calculation. You need to show, using the rules of gravity and quantum field theory, that the entanglement entropy of Hawking radiation actually does turn over and come back down. And nobody could do it. For 25 years, nobody could do it. Every time you tried to compute the entropy of the radiation using Hawking's methods, you got the wrong answer. The entropy just kept going up. And then, in 2019, two groups of physicists independently cracked it. One group was led by Jeff Pennington at Stanford, and the other included Ahmed Almhiri, Netta Engelhardt, Donald Merolf, and Henry Maxfield. And the way they did it is genuinely beautiful. One of those moments where a new idea makes everything click into place in a way that feels almost inevitable in hindsight. The key insight involved something called the quantum extremal surface. This is a generalization of an older idea, the Ryu-Takayanagi formula, which came from the holographic principle and ADS/CFT. The Ryu-Takayanagi formula tells you how to compute entanglement entropy in a holographic theory. You find a particular surface in the bulk spacetime, the minimal surface, and its area gives you the entropy. It's a beautiful geometric translation of the quantum information concept. The quantum extremal surface prescription extends this by including not just the area of the surface, but also the entropy of quantum fields on one side of it. And here's where it gets interesting. When you apply this prescription to an evaporating black hole, something dramatic happens at the page time. Early in the evaporation, the quantum extremal surface that gives you the smallest entropy is empty. It's trivial, just a point. And the entropy you compute matches Hawking's ever-rising answer. But at the page time, a new quantum extremal surface appears. It sits just inside the event horizon of the black hole, and this new surface gives a smaller entropy than the old one. The rules say you should always pick the surface that gives the smallest entropy, so at the page time, you switch to the new surface. And when you do, the entropy starts decreasing. It follows the page curve. It comes back down. Information is conserved. Now you might be thinking, okay, but what does this actually mean physically? What's happening at the page time that makes this new surface appear? And this is where it gets really deep, because the answer involves something called an island. The region of spacetime between the new quantum extremal surface and the singularity, the interior of the black hole, basically, is called an island. And the calculation says that this region, even though it's behind the event horizon, is actually encoded in the radiation that's already escaped. The island is part of the entanglement wedge of the radiation. In the language of quantum information, The Hawking radiation has enough information in it to reconstruct what's happening inside the black hole, at least in that island region. This is remarkable. It means the interior of the black hole isn't as isolated as you'd think. The information about what fell in isn't trapped forever behind the event horizon. It gradually becomes accessible in the radiation, and the island formula gives you a precise, quantitative way to track how that happens, and the page curve falls out naturally without having to assume anything about the microscopic details of quantum gravity. You just need semi-classical gravity, Einstein's equations plus quantum fields, applied carefully with the right entropy prescription. Let that sink in for a moment. For decades, the information paradox seemed to require a complete theory of quantum gravity to resolve. People thought you'd need to understand the Planck scale physics, the string theory details, the loop quantum gravity corrections, whatever the final theory turns out to be. But the island formula suggests that the broad answer, yes, information comes out, yes, the page curve is correct, can be derived from principles we already understand, applied more carefully than anyone had done before. The details of the microscopic theory matter for the fine-grained questions, but the overall shape of the answer is robust. And here's what's really wild about this. The island formula has connections to almost everything we've talked about tonight. It uses the holographic principle, which came from Bekenstein, and Hawking's work on black hole entropy back in the 1970s. It uses the Ryu-Takayanagi formula, which came from ADS/CFT and string theory. It's consistent with the ER equals EPR conjecture, because the islands can be understood as being connected to the radiation through subtle geometric bridges. It vindicates Bekenstein's original intuition that black holes carry real entropy and real information. And it gives a concrete, calculable answer to the question that has haunted theoretical physics since Hawking's 1975 paper. Does information survive? The answer, as far as we can tell in the mid-2020s, is yes. Information is not destroyed by black holes. The page curve is correct. Unitarity holds. But, and this is important, we still don't fully understand how it happens mechanically. The island formula tells you that information comes out in the Hawking radiation, but it doesn't give you a detailed, moment-by-moment account of the physical mechanism. It's a bit like knowing that a magician's trick has a rational explanation without being able to see exactly how the sleight of hand works. The broad answer is clear, but the fine print is still being written. And that's okay. That's how physics works. You don't solve everything at once. You make progress in layers, each generation peeling back another layer of the onion, getting closer to the core. Michel and Laplace imagined dark stars. Einstein gave us curved space-time. Schwarzschild found the geometry. Chandrasekhar showed that stars could collapse. Oppenheimer and Snyder showed what that collapse looked like. Wheeler gave us the name. Penrose proved singularities were inevitable. Hawking showed black holes weren't completely black. Bekenstein showed they carried entropy. 't Hooft and Susskind gave us the holographic principle. Maldacena gave us ADS/CFT. Strominger and Vafa counted the microstates. And now Pennington, Almheri, Engelhard, Merolf, and Maxfield have shown us the page curve. Each step built on everything that came before, and each step revealed something that the previous generation couldn't have imagined. And there's still so much we don't know. We don't have a complete theory of quantum gravity. We don't know what replaces the singularity at the center of a black hole. We don't know whether the fuzzball picture is right, or whether Planck stars bounce, or whether space-time is fundamentally made of discrete causal sets or spin foam or emergent from quantum error-correcting codes. We don't know what happens to you if you actually fall into a black hole, whether you hit a singularity, pass through a firewall, dissolve into fuzz, or experience something we haven't even conceived of yet. These are open questions, real questions, questions that the smartest people in the world are working on right now, as you lie here in the dark. But here's what we do know, and it's worth holding on to as you drift off. We know that gravity curves space-time. We know that enough mass in a small enough region creates an event horizon, a boundary from which light cannot escape. We know that black holes are real. We've seen their shadows, heard their mergers in gravitational waves, watched stars orbit them. We know they carry entropy proportional to their surface area, not their volume, which hints at something holographic about the nature of reality. We know they radiate, slowly, over unimaginable timescales. And we know, or at least we're now quite confident, that the information that falls into them is not lost forever, but is gradually, subtly, encoded in that radiation, preserving the fundamental unitarity of quantum mechanics. That's a lot. That's an extraordinary amount to know about objects that, just 100 years ago, most physicists thought were pure mathematical fiction. And every piece of that knowledge came from people, real people, with real lives, who stayed up late and argued and made mistakes and tried again. John Michell, the quiet rector in Yorkshire, who imagined dark stars 2 centuries before anyone took the idea seriously. Karl Schwarzschild, solving Einstein's equations in the trenches of the First World War, dying before he could see what his solution meant. Subrahmanyan Chandrasekhar, a 20-year-old on a steamship, working out the fate of stars with a pencil and paper, then enduring decades of dismissal from Eddington before being vindicated. Roger Penrose, doodling on a napkin while crossing a street in London, realizing in a flash that singularities were inevitable. Stephen Hawking, told he had 2 years to live, going on to transform our understanding of the universe. Jacob Bekenstein, a young graduate student bold enough to tell Hawking he was wrong about entropy. Kip Thorne and Rai Weiss and the LIGO team spending 40 years building an instrument sensitive enough to detect a ripple in space-time smaller than a proton. Katie Booman and the Event Horizon Telescope collaboration, stitching together data from telescopes around the world to photograph a shadow 55 million light-years away. These are human stories. They're stories about curiosity and stubbornness and the strange, beautiful compulsion to understand. And the thing about black holes is that they keep rewarding that compulsion. Every time we think we've understood them, they reveal another layer, another surprise, another connection to something deeper. They are, in a very real sense, the universe's way of telling us that there's always more to learn. So as you lie here, letting your thoughts slow down, letting the day fall away, maybe hold on to one image. Imagine the night sky, impossibly vast, scattered with stars. And somewhere out there, hidden among those points of light, there are regions where space-time curves so deeply that it folds in on itself, where time and space trade rolls, where the laws of physics as we know them reach their limits, and something new, something we don't yet understand, takes over. They're out there right now. The supermassive one at the center of our own galaxy, 4 million times the mass of the sun, quietly sitting there while stars wheel around it. The billions of others scattered throughout the observable universe. The ones merging right now, sending gravitational waves rippling outward at the speed of light, waves that will pass through this room, through you, stretching space by less than the width of an atom, unnoticed but real. They're the strangest things in the universe, and they're also, it turns out, the most important clues we have about what the universe actually is at its deepest level. And we're still figuring it out. The story isn't over. But for tonight, that's enough. That's more than enough. Let it all go, soft and blurry. Let the black holes do their thing out there in the dark. You've spent a good while thinking about them, and now it's time to let your mind wander wherever it wants to go. Maybe to the edge of an event horizon, maybe to the quiet hum of Hawking radiation, maybe nowhere at all. Whatever comes, let it come easy. The universe will still be there in the morning, strange and beautiful and full of things we haven't figured out yet. And that's a good thing. That's the best thing. Good night.